Check one. Check one. Check one. Right. Hello, everybody. Back again with our night session. And today, with this, we are completing our 2024-2025 O-level batch. Before we start, confirm me from your end. Is all the duos perfect? All okay, na? Right, YouTube. All right. Perfect. Perfect. Yeah, that's how it is. Usually, if there is something important happening, initially at the beginning, my mic doesn't work. Last year, physics night also, when we started, for the first 30 seconds, mic didn't start. Mic didn't work. It is, right? First important things, last important things, mic doesn't work. That's usual. That's usual. Ha! Um, එහෙනම් ළමයි එහෙනම් ළමයි first we will start because today there is a section to cover. First we will start. Meanwhile, I'll talk to you on. Meanwhile, I'll talk to you on. Meanwhile, talk to you on. Hurry. Today the section is ළමයි. I want to finish a full section. Today the section is, the plan is to quickly revise electromagnetism. That's how I usually finish off the last is electromagnetism. Last year electromagnetism transformer section we did. May full electromagnetism we are going to come. Right? Electromagnetism and electromagnetic induction. Electromagnetism and electromagnetic induction. Not a big thing. Not a big thing. Listen now. Now itself we memorize, put the things into the mind. Now itself, whatever they are to memorize, we put the things to the mind. So sit properly, listen carefully, put the things to the mind now itself. On electromagnetism and electromagnetic induction lesson. Under this lesson, Lamai, there are 4 sections you will be learning. Number 1, we learn about magnetic effect of current carrying conductor. Magnetic effect of current carrying conductor. First section. Second section you learn about force acting in a current carrying conductor placed in a magnetic field. Force acting in a carrying conductor placed in a magnetic field. This heading looks a bit longer. Happy section is very simple. Third section you learn about electromagnetic induction. And finally, you learn about diugo transformer. Those are the 4 main sections. We'll start with the first one. Magnetic effect of current carrying conductor. First section, magnetic effect of current carrying conductor. Listen very carefully. Magnetic effect of current carrying conductor. Magnetic effect of current carrying conductor. Right. What is this telling us? If you have a current carrying conductor, if you have a current carrying conductor on, this is a conductor, this conductor is carrying some current. This is current carrying conductor. If you have a current carrying conductor, around the conductor, you call it vicinity of the conductor. Around the conductor, there you go. Around the conductor, in the vicinity of the conductor, there will be a magnetic field. Around the conductor, in the vicinity of the conductor, there will be a magnetic field. Basically, around a current carrying conductor, there is magnetism. Usually the symbol for magnetic field is my capital B. That's the usual symbol. Now I'm not going to use those symbols. For you all to simply understand, I wrote it as M. Around a current carrying conductor, that means in the vicinity of the conductor, there is a magnetic field. Any conductor you take, it's like this. Now, for example, if you look at my ugly phone charger, the most ugliest phone charger, all the devices I have, they are full of markup and inks. This phone charger. White color charger. White color charger. එතකොට ළමයි, in this charger, if there is current flow, let's say I connect it to the plug point, there is current flow. If there is current flow around the conductor, around the charger, in the vicinity of the charger, there will be a magnetic field. Around the charger, in the vicinity of the charger, there will be magnetic field. Any conductor like that. Now look at your, what the device that you are using. Yes, they are. Around those wires, there is magnetic field. That's the theory telling us. Around a current carrying conductor, there is magnetic field. Okay. Now, how to find the direction of this magnetic field? How to find the direction of this magnetic field? Two rules are there. One, Maxwell's corkscrew rule. Two, right hand grip rule. Maxwell's corkscrew rule and right hand grip rule. What I recommend is use right hand grip rule. Don't use Maxwell's corkscrew rule. It's a bit confusing if you try to apply it in normal scenario. So best is you can use right hand grip, but know both the rules. What is Maxwell's corkscrew rule telling us? Now first, have you seen a corkscrew? Corkscrew. It's a device like this. Handle is there. It has a screw-like thing. Usually to open bottles that has a wooden lid, you call it a cork. The bottles that have a cork on it, to open it, what they do is they use this corkscrew. Take, this is the bottle. Now this bottle you don't need a corkscrew, but just imagine here you have a wooden lid. To open it, you take the corkscrew, keep it on top, then you rotate it. When you rotate it, it will go down. Why? It has a screw-like thing. Just like you keep a nail, a screw nail and rotate it. When you keep a screw nail and rotate it, it goes in. When it goes in, you hold it from the handle, then you pick it up. You hold it from the handle, then you pick it up. That way you can open it. That's a corkscrew. Now using this fellow is making a rule to find the direction of magnetic field when you know the direction of current flow. What is this fellow telling us? You place the tip of the corkscrew in the direction of the current flow. You place the tip of the corkscrew in the direction of current flow. On current is flowing downwards, so you place your tip of the corkscrew downwards. You place the tip of the corkscrew in the direction of current flow. Now, if I want to send the tip down, I need to rotate this corkscrew. If I want to send the tip down, I need to rotate this corkscrew. Which direction I need to rotate? Which direction I need to rotate? I need to rotate it in clockwise direction. I need to rotate it in clockwise direction. And that's the direction of magnetic field. You send the tip of the corkscrew in the direction of current flow. To send the tip of the corkscrew in the direction of current flow, you need to rotate the handle there. Which direction you rotate it, that gives the direction of magnet. You need corkscrew and all. Take a bottle, take a bottle, take a bottle. This lid. If I want to send the lid down, I need to rotate it clockwise. If I want to send the lid down, I need to rotate it clockwise. And if I want to send the lid down, why down? That's the direction of the current flow. I need to rotate it clockwise. And clockwise is the direction of magnetic field. That's the direction of magnetic field. That is Maxwell's corkscrew rule. That is Maxwell's corkscrew rule. Don't use it much because sometimes it is confusing. Why confusing? Let's take in the exam, we give a conductor like this. Current is flowing in this direction. Now for some people, it's hard to think which direction you need to rotate. It's hard for you to think. Now you need to take the lid out. To take the lid out, which direction you rotate? Anti-clockwise you need to rotate. Anti-clockwise you need to rotate. But it's a bit hard for you to think in the exam environment. So don't use this much in the exam. If you have already got used to using this rule, use it. Otherwise, don't use it because there's an easy rule, right hand grip rule. What is right hand grip rule telling us? What is right hand grip rule telling us? Let's take you have a conductor carrying current in this direction. You take that conductor on your right hand, eating hand. You take that conductor on your right hand such that the thumb points the direction of current flow. You take that conductor on your right hand such that thumb points the direction of current flow. Now current is flowing that direction, you take it this way. Then your other four fingers will show the direction of magnetic field. Other four fingers will show the direction of magnetic field. If I do it to the camera, current is flowing that direction. You keep your thumb in that direction. Then my other four fingers, from top it is coming out. From top out, from bottom in. Top out, bottom in. Top out, bottom in. That's the direction of magnetic field. Top out, bottom in. That's the direction of magnetic field. Top out, bottom in. That's the direction of magnetic field. There are symbols we use to represent out and in. Out is usually represented by circle and a dot. Circle and a dot means out. In is usually represented by circle and a cross. Circle and a dot means out. Circle and a cross means in. Don't go to memorize both of them. Memorize only one. That also simply memorize like this. See, if this pen is coming out of the board, look at this pen and tell me what you see. If this pen is coming out of the board, look at this pen and tell me what you see. Can you see a dot? If this pen, I'll use a smaller pen. If this pen is coming out of the board, what do you see? Can you see a circle and a dot? So circle and a dot can out. Circle and a dot can out. Other one is in. Magnetic field out from top, in from bottom. That's right hand grip rule. That's way more easy. Way more easier. Example see. Conductor, current flowing that direction. Conductor, current flowing that direction. Apply right hand grip rule. You take the conductor on your right hand, eating hand. Then you place your thumb in the direction of magnetic field. You place your thumb in the direction of current flow. On current flow this direction, you place your thumb this direction. Place your thumb this direction. Place the thumb this direction. Now see, From top, my hand is going in. Can you see that? From top, hand is going in. Fingers are going in. Top in. My normal human being. Top in can bottom is guaranteed. What? If fingers go in from top, guaranteed from bottom, what? Out. Normal human being. That's how we behave. No, you can't send hand in from top and bottom both. No, top in can anything bottom out. Top in, bottom out. Top in, bottom out. Out, always memorize the out symbol. Out symbol is very easy. Out can, it's coming out. If it is coming out, you see a circle and a dot. In, circle and a cross. Yeah, theory class people, we have done this using Borlugoda and Galpath. Borlugoda and Galpath. On, you all do. Current display in that direction. Tell me at point A, in or out. Magnetic field at point A, in or out. Apply and tell me. Magnetic field from point A, in or out. Huh. See, take the conductor on your right hand. Take the conductor from your right hand such that your thumb points the direction of current flow. Thumb points the direction of current flow. Thumb points the direction of current flow. Thumb is pointing direction of current flow. Then from top, where? From top, what's happening? Out. Top, out. Top, out. Top, out. Top, out. Top, out, circle and a dot. Then from bottom in, circle and cross. Bottom in, circle and cross. Where is it? So apply right hand grip rule. It's way more easier than Maxwell's corkscrew rule. It's way more easy. Okay. Hurry. That's what first theory telling us. That's what first theory telling us. Magnetic effect of a current carrying conductor. More simple action. If you have a current carrying conductor, in the vicinity of the conductor, there will be a magnetic field. In the vicinity of the conductor, there will be a magnetic field. You find the direction of that magnetic field. I'll write only one rule and keep there. Right hand grip rule. Right hand grip rule. Using right hand grip rule, you can find the direction of the magnetic field. On, going to the second theory. Going to the second theory. Force acting in a current carrying conductor placed in a magnetic field. Force acting in a current carrying conductor placed in a magnetic field. Force acting in a current carrying conductor placed in a magnetic field. Force acting in a current carrying conductor placed in a magnetic field. Force acting in a current carrying conductor placed in a magnetic field. Heading is a bit long. No? What I will do is, I'll break the heading into several parts. I'll break the heading into several parts. Force acting, for now we'll keep it away. Or force acting part, we'll keep it away. Current carrying conductor. We already know about current carrying conductor. Just now we learned. Placed in a magnetic field. Discuss about these two first. Current carrying conductor. What do you know about current carrying conductor? What you know about current carrying conductor? What you know about current carrying conductor? Tell me. Around it, what is there? Around it, what is there? Dingala, tell me. Around it, what field is there? Just now we learned. Magnetic field is there. Around a current carrying conductor, magnetic field is there. That is what we just now learned. Around a current carrying conductor, there is magnetic field. Around it, there is magnetic field. Around a current carrying conductor, you have a magnetic field means lamai. This current carrying conductor is just like a magnet. Around a magnet also. Around a magnet also. Around a magnet also. Around a magnet also. You have what? Magnetic field. Around a magnet, you have magnetic field. Around a current carrying conductor, you have magnetic field. Means I can tell current carrying conductor is just like a magnet. Agree? Agree with what I tell? Around a current carrying conductor, you have magnetic field. Around a magnet, you have magnetic field. That means current carrying conductor is just like a magnet. Now, from your childhood, from your grade 1, grade 2 childhood, if you keep a magnet closer to another magnet, let's say this magnet is kept closer to another magnet, north and south are kept closer, what will happen? This magnet kept closer to this magnet, north and south are kept together. These things don't get wrong, eh? Grade 6 work. Grade 6 you have magnets. North and south are kept closer. They attract. That means when north and south are kept closer, there is an attraction force. There is the attraction force. Attraction is there. If I keep the other way, now what is there? Will happen. Repulsion will happen. Repulsion will happen. When south and south are kept closer, there is repulsion. That means there is repulsive force. That means when one magnet is kept closer to another magnet, there is either attraction force or repulsion force. If I summarize that, when two magnets are kept closer, there is a force acting. When two magnets are kept closer, there is a force acting. Agree? Now, one step ahead. I already told you current carrying conductor is just like a magnet. Current carrying conductor is just like a magnet. Why? Around a current carrying conductor, you have magnetic field. Around a magnet also, you have magnetic field. Current carrying conductor is just like a magnet. Now, if I replace this real magnet with a current carrying conductor, onna puta. Current carrying conductor is just like a magnet. That means I have kept a magnet here. Closer to another magnet. Same magnet closer. What is going to act? Magnet closer. What is going to act? Dingala, tell me. Magnet closer. What is going to act? Force will act. That means I can tell when a current carrying conductor is placed closer to magnetic field, a force will be acting. Look at the words I'm using. When a current carrying conductor is placed closer to a magnetic field, force will be acting. A current carrying conductor is just like a magnet. Why? Around a current carrying conductor, a magnetic field. Current carrying conductor is like a magnet. You keep one magnet closer to another magnet. Great child force when two magnets kept closer, force will be acting. So two magnets are kept closer, force will be acting. Current carrying conductor is just like a magnet. When current carrying conductor is kept closer to another magnet, force will. When a current carrying conductor is placed in magnetic field, force will be acting. Agree? Agree? Huh. Now read the heading. Now read the heading. Louder, louder. Read the heading. Force acting in a current carrying conductor placed in magnetic field. Hari ni lamai. Eating when a current carrying conductor is placed in magnetic field, what is going to act? Force will. That's the heading telling us. That's the theory. Force acting in a current carrying conductor placed in magnetic field. When a current carrying conductor is placed in magnetic field, force will be acting. That's second theory. That's the second theory. So you can see second theory is an integration of the first theory. First theory is telling around a current carrying conductor, a magnetic field. Second theory, an integration of it. When that current carrying conductor is placed closer to another magnet, there will be a force acting. Heading tells us the full story. Force acting in a current carrying conductor placed in magnetic field. Oh, yes, yes. Think according to the heading, force will be acting in a current carrying conductor placed in magnetic field. That's the theory. But one point, one important point. For this force to act, the current flow should be perpendicular. Perpendicular කියන්නේ 90 degrees. Perpendicular to the magnetic field. Current flow should be perpendicular to the magnetic field. Only then a force will be acting. Only then a force will be acting. And force acting is also going to be perpendicular to the other two components. Force acting is also going to be perpendicular to other two components. Force is also perpendicular. Current, magnetic field, force, all three are perpendicular. All three are perpendicular. Huh. If you know the direction of current flow and the direction of magnetic field, can you find the direction of force? If you know the direction of current flow, direction of magnetic field, can you find the direction of force? Yes, you can. How to find the direction of the force there? How to find the direction of force there? That is where Fleming's left hand rule comes into play. Fleming's left hand rule comes into play. Remember, left hand will come first. After that only Fleming's right hand rule will come. Always keep in mind in that order. Fleming's left hand rule, left hand part will only come first under the Fleming section. After that only we discuss about right hand rule. Hurry. What is Fleming's left hand rule telling us? You know the direction of current flow. You know the direction of magnetic field. You are going to find the direction of force. How to do that? Take your left hand. Place your index finger to the direction of magnetic field. Index to the direction of magnetic field. And middle finger to the direction of current flow. But make sure that they are perpendicular to each other. Middle finger direction of current flow. When you open your thumb will point the direction of force. Thumb points the direction of force. If I drew and show, you take your left hand and adjust the index to the direction of magnetic field. Into the direction of magnetic field. Middle finger to the direction of current flow such that both of them are perpendicular to each other. Open the thumb, don't adjust the thumb, open the thumb, it shows the direction of force. Shows the direction of force. It shows the direction of force. We'll do some questions. We'll do some questions. Conductor is there, current is flowing that direction. Current is flowing that direction. Nah, we'll take magnetic field. Magnetic field that direction. Current is coming out of the boot. Current is coming out of the boot. They are asking us to find the direction of force. Magnetic, you know, current, you know, they are asking you to find the direction of force. What's the rule? Now, once when you see this, magnetic, you know, current, you know, force, they are asking, can I Fleming's left hand rule? They won't tell you to use Fleming's left hand rule. You should know. Magnetic, you know, current, you know, then what's the rule? Fleming's left hand rule. Huh. Apply Fleming's left hand rule. Index to the direction of magnetic field on. Index that direction. Of current flow, current is coming out of the boot. Current is coming out of the boot. Middle out of the boot. Open the thumb. If you are a normal human being, the thumb will be upward. Thumb is upward. Then the force is up. Force is up. Huh? Will work for the second one? Will work for the second one? Magnetic field that direction, current is out of the boot. What's the direction of force? Apply. Left hand, be careful with the left hand. If you change the hand, then whole story will turn upside down. Left hand. Magnetic field that direction. Index that direction. Index that direction. Current is coming out of the boot. Current is coming out of the boot. Now, normally, if you open your middle finger is into the boot. You need to take it out of the boot. Always rotate from down. Don't rotate from top. You actually can't rotate from top. You have to bend your full self. Don't rotate from top. Rotate from down. Now, some fellows, even down, they can't rotate. Even down, they can't rotate. They bend their hand like this. If you bend your hand like this and try to rotate, you become like a Hansabag fellow. Hinda, you can't rotate it this way. Stretch your hand. Rotate from down. Stretch your hand. Rotate from down. Stretch your hand. Rotate from down. Where's the thumb pointing? Where's the thumb pointing? Downward. Thumb is pointing downward. Thumb is pointing downwards. Force is down. Force is down. Force is down. That is the second theory. That's it. One more point. What are the applications of it? This application part, usually they ask in the MCQ questions, say in the memorize and keep. Applications of force acting in a current carrying conductor placed in magnetic field. What are the applications? One, loudspeaker. Loudspeaker. Two, DC current motor. Loudspeaker, DC current motor. These devices, they work according to force acting in a current carrying conductor placed in magnetic field. Force acting in a current carrying conductor placed in magnetic field. Or that's it. Second theory. That's it. Our second theory. I'll write the rule in front and keep. For second theory, what's the rule we apply? Second theory, what's the rule? Fleming's left hand rule. Second theory, we apply Fleming's left hand rule. Left will come first. After that only we go to the right. Third, electromagnetic induction. Electromagnetic induction. Electromagnetic induction. Electromagnetic induction. Electromagnetic induction is the opposite of third theory. Electromagnetic induction is the opposite of third theory. Opposite of second theory. Now, what is the second theory telling us? What's the second theory telling us? This theory. What's the second theory telling us? When a current carrying conductor is placed in magnetic field, what is produced? Force. What second theory telling us? Current carrying conductor placed in magnetic field, force is produced. Second theory is telling us current carrying conductor placed in magnetic field, on force is produced. Force is produced. Induction is the opposite of it. Induction is the opposite. Now you are going to tell me. If I give a force, before force was produced, now I am giving force to a conductor placed in magnetic field. Force is given, magnetic field is there. Ehnan guess and tell me what is going to be produced. What is going to be produced? What will be produced? Current will be produced. Current will be produced. That's electromagnetic induction. When a force is given to a conductor placed in magnetic field, current is produced. Force is given, can you move a conductor? When you move a conductor, you can give a current, give a force. You move a conductor placed in magnetic field, current will be produced. You move a conductor placed in magnetic field, current will be produced. Move a conductor placed in magnetic field, current is produced. Current is produced. Current is produced. But two important points. One, for this current to be produced, direction of the force and direction of the magnetic field should be, fill the blank, should be the same previous thing. Perpendicular. Direction of the force and direction of the magnetic field should be perpendicular for the current to be produced. And direction of the current produced is also going to be perpendicular to each other. Perpendicular to each other. All three are perpendicular. Are the same previous two. Okay. Plus, between the conductor and the magnetic field, there should be a proper motion. You call it a relative motion. There should be a proper relative motion between the conductor and the magnetic field. Now, for example, let's take this is the conductor, this is the magnet. There should be a motion between them, a relative motion. Now, when I move the conductor like this is the magnet, this is the conductor. Right? If I move the conductor like this, there is a force, there is current produced. If I move the magnet like this also, there is a force, current is produced. If I move it like this, if I move it like this, magnet and the conductor, there is a force, there is a motion, current is produced. If I move it like this, between the magnet and the conductor, there is a force, current is produced. If I move it like this, now look, yeah? If I move it like this, Tell me, between the conductor and the magnet, is there a motion? Between the conductor and the magnet, is there a motion? I am moving. Everything I am moving. But between them, is there a motion? Ah, no motion. If there is no motion between them, then no current. Between them, there should be a motion. Between them, like this, like this, like this, like this. There should be a motion between them. Between them, if there's a motion only, there will be current produced. Now, these things we have done it in theory class, and theory people know the story behind it. Huh. So that point keep in mind. What's the rule? Now you know. Previous one, Fleming's left hand rule kiyanne. This one, right hand rule. Fleming's right hand rule. Fleming's right hand rule. Story is the same. If you know the direction of force, now force direction you know, and you know the direction of magnetic field, you can find the direction of current. If you know the direction of force and the direction of magnetic field, you can find the direction of current. How? Always remember your index finger is magnetic field. On right hand, take the right hand, index shows the direction of magnetic field. Thumb is always the direction of force. Thumb, force. They should be perpendicular, right? Thumb, force. These two you know. Force you know, magnetic field you know. Index magnetic field, thumb force. Now you open your middle finger, keeping it perpendicular to each other. Open your middle finger. Middle finger will show the direction of current. Middle finger shows the direction of current. Middle finger shows the direction of current. If I draw and show, if I draw and show, thumb points the direction of force. Thumb points the direction of force. Index points the direction of magnetic field. These two you adjust. After adjusting those two, you open your middle finger. Middle finger will show the direction of current. Middle finger shows the direction of current. But with your right hand. Let's take magnetic field is that direction. Force is given in that direction. Magnetic field direction, force that direction. We'll find the direction of current. Magnetic field that direction, force that direction. We'll find the direction of current. On right hand, and be careful, right hand. Index towards the magnetic field. Index in the magnetic field. I'll do it to the camera. Index to the magnetic field. Thumb to the direction of force. Thumb to the direction of force. Now you open your middle finger. Open the middle finger. On. Middle finger is in. Middle finger in. So the current is into the boot. Current is into the boot. Into the boot. That'll work. Find me the direction of current flow. Direction of current flow. Right hand, your index to the direction of magnetic field. Index to the direction of magnetic field. Magnetic field that direction, index that direction. Index that direction. Index that direction. Thumb to the direction of force. Thumb to the direction of force. Thumb to the direction of force. You turn your thumb down. Don't turn it from the other side. This side you can't. You can't. Stretch it and turn. Only this side you can. From this side. Open the thumb. Open the middle finger. You can't see properly. Middle finger is in. Middle finger in. Again, see how I did? Ta-tan. Tap. So, so your middle finger is in. Circle and a cross. Current is in. On. Little different, eh? Little different. Work. Perfect. Right. Index is magnetic field. Index is magnetic field. Magnetic field is up. Index is up, Lamai. Index is up. Index up. Now your thumb should point the direction of force. Force is that way, neither. Force is that way. This is the way. This is the direction. I do it this. Force is this way. Force is this way. Now you open your middle. Open the middle. Middle this way. Again, see how I did? Index up. See? Magnetic field is there. Index up. Now when I open the thumb, now this way if I do it, now my thumb is directly that way. Thumb is that way. Open the middle. Middle out. Middle out. Out of the boat. Out of the boat. Circle and across. Do one more. Think and do. Think and do. Ah. Now see. Analyze the question. What is going in? Magnetic is in. Magnetic is in. Can your index is in. Index is in. Index in. On. Index in. Force is this direction. Force is this direction. Thumb should be this direction. Thumb should be that direction. Thumb should be that direction. Now you open your middle. Where is the middle? Where's the middle? Middle down. See? Magnetic is into the boot. Magnetic in. Force is that direction. Force is that direction. Now you open your thumb. Thumb is down. Thumb is down. Thumb is down. Sorry, you open your middle finger. Middle finger is down. Middle finger is down. Down. Hey, me red color is becoming blue, white color. That's the direction of the current. Hurry. Index in. Do with me, do with me. Don't look at this and do separately. Index in. Index in. Thumb that direction. thumb that direction. You open your middle down, middle down, middle down. Correct? So that's the direction. That's electromagnetic induction. One more point. What are the uses? What are the applications? Application. Applications. What are the applications? What are the applications? Number one, this is used in uh, AC current, AC current dynamo. Used in AC current dynamo. Two, bicycle dynamo. Three, moving coil microphone. Moving coil microphone. Again, open the mouth and tell. Electromagnetic induction. What are the applications? AC current dynamo, bicycle dynamo, moving coil microphone. Again, louder. AC current dynamo, bicycle dynamo, moving coil microphone. Yeah, even yesterday we touched that. Even yesterday we touched. Hurry, that's it, electromagnetic induction. I'll write the rule in front. Fleming's right hand rule. Fleming's right hand rule. Fleming's right hand. Again, repeat the rules. Magnetic effect of current carrying conductor. Can remember? Current carrying conductor, around it you will have magnetic field. What's the rule? Right hand grip rule. Again, louder, louder, louder. Magnetic effect of current carrying conductor, around a conductor you have magnetic field. What's the rule? Right hand grip rule. Second, force acting in a current carrying conductor placed in magnetic field. Force acting in current carrying conductor placed in magnetic field. Fleming's first rule. Fleming's first rule is left. Fleming's left hand rule. Fleming's left hand rule. Fleming's left hand. Third, are opposite one, where you produce current. Electromagnetic induction is right hand. Fleming's. Finally, transformer. Finally, transformer. Final section, transformer. Onnalamai, you have two types of transformers. Two types of transformers. These things you all know. Step up transformer. Step up transformer. Step down transformer. Step down transformer. In a transformer, you have two coils. You have two coils. You have two coils. One is called as primary coil. One is primary coil. The other is called as secondary coil. Secondary coil. A step up transformer, number of turns in primary coil is less than number of turns in secondary coil. Number of turns in primary coil less than number of turns in secondary coil. Number of turns is represented as capital N. Number of turns in primary is less than number of turns in secondary. And what will step up transformer do? Step up transformer will increase the voltage. It increases the voltage. It increases the voltage. That means voltage in primary is less than voltage in secondary. Voltage is increasing. Voltage in primary less than voltage in secondary. Step up transformer. On the other hand, step down transformer. Step down transformer. On. Two coils are there. One coil is the primary coil. One coil is the primary coil. The other coil is the secondary coil. The other coil is the secondary coil. If you look at the number of turns in primary and secondary, number of turns in primary coil greater than number of turns in secondary coil. Primary big, secondary small. Number of turns in primary is larger than primary number of turns in secondary. And voltage in primary is greater than voltage in secondary. Voltage in primary greater, voltage in secondary less. Voltage decreasing. Voltage is decreasing. Voltage decreasing. Step up transformer will increase the voltage. Step down transformer will decrease voltage. Step up transformer, number of turns are increasing. Voltage is increasing. Step down transformer, number of turns are decreasing. Voltage is decreasing. Voltage is decreasing. Equations. Two main equations are there in a transformer. Number of turns in primary over number of turns in secondary is equal to voltage in primary over voltage in secondary. Number of turns in primary over number of turns in secondary is equal to voltage in primary over voltage in secondary. First equation. Second equation. Voltage in primary multiplied by current in primary is equal to voltage in secondary multiplied by current in secondary. Voltage in primary multiplied by current in primary. Voltage in secondary multiplied by current in secondary. Voltage in secondary multiplied by current in secondary. Okay. Okay. Those are the important points. Other than that, few more important points I will give. Remember, in a transformer, if the transformer is 100% efficient, if the transformer is 100% efficient, the total power you give as the input is the same power you get as the output. Whatever the power you give as the input is the same power you get as the output. Say you 1000-watt power as the input power, you get 1000-watt power as the output power. If the transformer is 100% efficient. Actually, whatever the transformers we discuss in our syllabus 100% efficient. So power input and power output are same, no change. Plus, in a step-up transformer, voltage is increasing. Voltage is increasing. I told you power is the same. Power is constant. Power equal voltage into current. Power is not changing. Input power and output power are same. Power is constant. Voltage is increasing. Then you all tell me what should happen to the current. Mathematically tell is one factor. What should happen to the other factor? One factor increasing, power is constant. What should happen to the other factor? On other factor should decrease. So remember, in a step-up transformer, current flow will decrease to keep the power constant. Current flow will decrease to keep the power constant. These things in theory classes, we have very deep have explained these. In step-up transformer, voltage increases, current flow will decrease. Step down, power equal voltage into current. Power is kept constant. Power is kept constant. You all tell me. Power is kept constant. In step-down transformer, voltage is decreasing. One factor decreasing to keep the other factor constant. To keep the final answer constant, what should happen to the factor? Is constant, voltage is decreasing. To keep power, what should happen to the current? Current should increase. Current should increase. So remember, in a step-down transformer, current flow will increase. Current flow will increase. It's the opposite of what is happening to the voltage. Opposite of what is happening to the voltage. And in a step-up transform, current is decreasing. Current is decreasing. Current is decreasing. Let's say you are giving about 100 ampere current. That is becoming 10 ampere from the other side. current is decreasing. Current is decreasing. Huge current is running through primary coil. Small current is going through secondary coil. See, current is decreasing. Big current is going through primary. Small current is going through secondary. Big current through primary. Small current through secondary. Big current through primary kiyanne lamai. Primary coil has to handle a large current. Primary coil has to handle a large current. You tell me, to handle a large current, what you should do to the thickness of the conductor? To handle a large current, what you should do to the thickness of the conductor? To handle a large current, what you should do to the thickness? Thickness should be in. To handle a large current, thickness should be increased. Then, instead of transformer, primary coil is made thicker. Primary coil is made thicker than the secondary coil. Why? Primary has to handle a large current. To handle a large current, you increase thickness. Small, chooty wires can't handle large current. No, you should have thick, big wires. So primary coil's thickness is increased compared to the secondary coil. Why? Then primary coil can handle a large current. I ask me, sir, if we don't do it, now let's say you use a chooty wire here, chooty small wire, used as the primary coil. Through that small wire, you are sending big current. What will happen to the wire? Through a small wire, if you try to send big current, what will happen to the wire? It will start sometimes burning. That means there will be heat generated. There will be a heat loss. Guaranteed there will be a heat. Heat will be generated. There will be a heat loss. Remember, in a transformer, you try maximum to reduce the heat loss. Not only in transformer, any device the same. Now, just imagine your laptop. Just after you switch it on, it gets heated to 100 degrees Celsius. Is there any use? No. So in devices, you need to reduce unnecessary heat loss. So to reduce that heat loss only, they have made it thicker. To reduce heat loss. Wire is made thicker. Primary coil is made thicker to reduce the heat loss. Come to step down. In step down, what is happening? Current is increasing. Let's say you are giving 10 ampere current. That ampere is becoming 100 ampere. You are giving 10 ampere, it's increasing, you are getting 100. You are giving 10 ampere, it's becoming 100 ampere. Then who is large current? Which coil is handling large current? Which coil is handling large current? Secondary coil is handling large current. To handle large current, what you should do to the thickness of the secondary coil? What you should do to the thickness of the secondary coil? Increase. Thickness should be increased. So secondary coil is made thick. Why? To reduce the heat loss. Secondary coil is made thick. Simply memorize it like this. Chooty is thick. Step transformer, primary is chooty, thick. Step transformer, secondary is chooty, thick. Chooty boy is thick. Primary is small, chooty one, it is thick. Secondary is small, chooty one, it is made thick. Chooty boy is made thick. Hurry. That's about transformers. One more point I wanted to give, make a dunnana hunda. They asked this section also. One more point. Force acting in a current carrying conductor placed in magnetic field. How to increase the amount of force produced? How to increase the force or how to change the force? How to increase the force or change the force? One, you supply a large current. You supply a large current, you can increase the force. Two, you can make a strong magnet. Use a strong magnet. That means you increase the magnetic field. Three, usually here the conductor is made into a coil. So what you can do is increase the number of turns in coil. Or you can make the coil a bit longer. Increase the number of turns in coil. Or you can make the coil a bit longer. I don't know why this is turning to white color after I write it. So by doing these three things, you can increase the amount of force produced. Send a large current, use a strong magnet, increase the number of turns in the coil. Even in induction, this story is applicable. Even in induction, even in induction, how to increase the amount of current produced? How to increase the amount of current produced? You are giving a force, no? When you give a force, you are actually moving that conductor. You are moving the conductor, you are giving a speed there. Increase the speed. Increase the speed. Now conductor, you are giving a force. You are giving a force, you are moving it. If you are moving it, you increase the speed. You increase the speed, or you can use a strong magnet. Again, you can increase the number of turns. Increase the number of turns in coil. Increase the number of turns in coil. That's it. Lesson done. Show the last slide. Hurry. This is for induction. Well, this for induction. Letters are too small. Okay. This for induction. Ne? And now I'll change for the other one. Force acting in a current conductor placed in magnetic field. This for force acting in a current conductor in magnetic field. Okay. Now take the question to you. I already sent you all. I didn't go to put lot of questions there, only about 3 questions. So because with 2 we have to discuss and finish it off. No? Again, we can't drag it at all. In the huh. This is last year's one. 2023 O level. 2023, 2020, 2023, 24. These people did it in 24, just like y'all. Huh. A magnetic field is created around a straight conductor carrying an electric current. That we know, no magnetic field is created around a straight conductor that is carrying electric current. A, using a diagram, illustrate the direction of the current flowing through such a conductor and also the shape and the direction of magnetic lines of force created by it. Using a diagram, illustrate the direction of the current flowing through such a conductor and also the shape and direction of the magnetic lines of force created by it. They are asking us to illustrate the direction of the current flow and the magnetic lines created by it. Huh? Worked out? Question 1. Question 1, A part. They are telling a conductor is carrying current. If a conductor is carrying current, around it magnetic field is there. Around it magnetic field is there. They are asking about the force as well. Using a diagram, illustrate the direction of the current flowing through such a conductor and also the shape and the direction of the magnetic lines of force created by it. You all tell me, if you have a current carrying conductor, with your wish you can draw whatever the way you want. If you have a current carrying conductor, in the vicinity of the conductor, around the conductor, what is there? In the vicinity of the conductor, that means around the conductor, what is there? Magnetic field. They're asking us to draw it using the shape, the correct shape. You can draw it this way. If I properly show the direction, that's the direction of the magnetic field. Always when you draw like this, Lamai, nearby that, draw the symbolic form as well. Draw the symbolic form as well. Huh? Current is flowing this direction, then magnetic field is around it. Magnetic field is around it. This way in. Current is flowing this way in, that way in, that way in, circle and a cross. This way out, circle and a dot. Circle and a dot. That's the magnetic field. That's the magnetic field. That's the magnetic field. Okay. That's the magnetic field. This can depend on your diagram. Maybe if you draw the conductor downwards, magnetic field will be the other way. If you draw the conductor this way, magnetic field that way. M can be there. M කියලා දාන්න එපා. Properly write it as magnetic field. You properly write it as magnetic field. Magnetic field. Properly write it as magnetic field. Simple question. B part. Present example for two instances where electromagnets are made by modifying the conductor as a coil and sending current. What are the instances where electromagnets are used? Electromagnets are used. They are asking about force acting in a current carrying conductor placed in magnetic field. The places electromagnets are used. What are the places force acting in a current carrying conductor placed in magnetic field is used? Loudspeaker, DC current motor. Those are the places. Even you can go out of the box and tell some more answers. Now, if you take cranes that lift metallic objects, in grade 7 or 8 or something you would have learned. Cranes that lift metallic objects. In that, what is there? Cranes that lift metallic objects, what is there? Electromagnet is there. So even those answers are applicable. Even those answers are applicable. However, here they are asking two instances. You can write these two. Roman 2. When a conductor carrying a current is placed perpendicular to a magnetic field, as shown in the figure, a force acts on it. Conductor is there, magnetic field is there. On. Now itself analyze the question. Conductor is there, a current is there, magnetic field is there, M is there. Lamai ehenang tell me, I is there, M is there. What will be produced? I is there, M is there. What will be produced? First question. Force will be produced. Force will be produced. Fleming's left or right? Fleming's left or right? Left hand rule. Why? We discuss about force first. Second, the electromagnetic induction, we discuss about current. For that only you have right hand rule. This one left hand rule. This one left hand rule. First analyze those things and start the question. When a conductor carrying current is placed perpendicular to a magnetic field as shown in the figure, a force acts on it. Okay, A part. State two factors affecting the magnitude of the force acting on the above conductor. What are the two factors that can affect the magnitude of the force? One, amount of current flowing. Two, strength of the magnet. Here you can't tell number of turns in the coil. Coil is not conductor is there. Maybe you can tell the length of the conductor. Here you can't tell the number of turns in coil and think and answer. Here you don't have a coil. You can't number. You can make it the other way. You can tell length of the conductor. So they are asking state two factors affecting magnitude of the force. One, amount of current flow. I'll write it separately. Roman two-way. Amount of current flow, and two, strength of the magnet. Strength of magnet, or you can tell strength of magnetic field. If I go one more step ahead, our number of turns in the coil is the length of the conductor. Length of the conductor. Okay. Name the rule used to find the direction of the force acting on the conductor. Allow me. Tell me the rule. See, look at the questions that are coming in the final O-level exam. What's the rule used to find the direction? On the Fleming's left hand rule. I'll just write it in short. You can't just write left hand rule, Fleming's left hand rule. As the question is easy, marking will be tough. So properly write it. Fleming's left hand rule. See part. Present examples for two instances in which force generated as above is made for use. Users of electromagnetic induction. Induction away, the force. This question. What are the places this force part is applied? Force acting in a current carrying conductor. The same answer need. Speakers, loudspeaker, same answer will come again. Loudspeaker, DC current motor. DC current motor. Here you can't write down are cranes. In crane, force not there. They are only electromagnet is there. They don't use a force or anything. In loudspeaker and DC current motor, you have an electromagnet. From that a force is generated. You can write DC current motor, loudspeaker. DC current motor, loudspeaker. Here you can't again write crane. C part. The production of electricity in a hydroelectricity power plant is based on principle of electromagnetic induction. Dingala, revise and tell me what's the rule? What's the rule? Fleming's right hand rule. Roman 1. Explain briefly what is electromagnetic induction. On time to write all your lies. Explain briefly what is electromagnetic induction. Start explaining what is electromagnetic induction. Don't panic. You start explaining it in your own words. What is electromagnetic induction? When a conductor placed in magnetic field is moved. Move means you are applying a force. When a conductor placed in magnetic field is moved, what is generated? What is generated? Current is generated. Current is generated. But you should be careful that you move it perpendicularly. That word also. When a conductor placed in magnetic field is moved perpendicularly, current is generated. When a conductor placed in magnetic field is moved perpendicularly, current is generated. If you write that, you will get marks. But actually speaking, their current is produced because of a EMF. At that instant, current is produced actually because of a EMF, electromagnetic force. Actually speaking, when you move a conductor placed in magnetic field, what is produced is a electromagnetic. Due to that electromagnetic force only, a current will be generated. So even you can directly write a EMF is generated. Even that turn, you are correct. So if I properly tell, if a conductor placed in magnetic field is set in motion perpendicular, electromagnetic force is generated. Conductor magnetic field is set in motion perpendicular, electromagnetic EMF is generated. Those who want to write down. When a conductor placed in when a conductor placed in when a conductor placed in magnetic field is magnetic field is magnetic set in motion perpendicularly, set in motion perpendicularly, set in motion perpendicularly. A electromotive force is generated. A electromotive force is generated. Roman 2 illustrates separately and graphically how electric current produced by a hydroelectricity power plant and electric current produced by a solar panel varies against time. Hydroelectricity power plant uses a dynamo to produce current. Remember, dynamo always produces AC current. Hydroelectricity power plant uses a dynamo produces AC current. Solar panel. Solar panel will produce current, store it in a battery, from that only we get the current. Current obtained from a battery is always DC. Keep that in mind. Current from dynamo is AC. Current from a battery is DC. They are asking, illustrate separately, graphically, how AC current and DC current varies. On. Can't you draw that? See Roman 2. Hydro power station. Hydro power station produces AC current. Voltage versus time. Your graph is this. Solar. Solar panel produces DC current. DC current. Your graph is this. Remember, always dynamo produces AC. Stored current is DC. Hydropower station AC. Solar panel DC. That's your graph. Huh. 2022. That's also a good question. B part. In figure 1, A, B, and C, D indicate two metal rails. A, B, and C, D are two metal rails. PQ is a conductor rod. This is a conductor rod, which can be slid on two rails. The resistance of the rails and the rod are negligibly small. A uniform magnetic field is applied into the plane perpendicular to it on which the metal rails are placed. This is the magnetic field. This cross is the magnetic field. When the rod PQ is moved to the right, an electric current is produced. When you move this to the right, when you move it, you are giving a force. Already magnetic field is there. Guaranteed current is produced. Okay. Roman 1. Name the rule which can be used to decide the direction of the induced current. Lamai, or same question. What's the rule you use to find the direction of current? Rule used to find direction of current. Right hand, Fleming's right hand. Fleming's right hand rule. Fleming's right hand rule. Roman 2. According to the rule stated in 1 above, does the current flow from P to Q or Q to P? We'll apply Fleming's right hand rule. Apply now. Force is this direction, magnetic field is into the boot. I'll separately draw it for you to easily apply. Force that direction, magnetic field is in. Apply, tell me. Apply Fleming's right hand rule and tell me. Directly tell me which direction is the current. Up or down, tell me. Later we'll change to P, Q, Q, P, all those things. What's the direction of current? First your index. Right hand index. Magnetic field into the board, index is in. Index is in. Index in. Next, thumb. Force is in that direction, thumb that direction. Thumb that direction. Thumb that direction. Now you open your middle finger is up. Middle finger is up. See? Magnetic in, index in. Force that direction, middle finger up. Middle finger up. Current flow is upward. Current flow is upward. Current is up. Current is up කියන්නේ ළමයි where to where? Current is up කියන්නේ Q to P නේද? Current is up කියන්නේ Q to P. Q to P. Q to P. Current is from Q to P. Q to P. Roman 3. Due to the induced current in PQ, only one of the LED labeled Y and W lights. What is the LED? Right. We'll draw the direction of current flow. We'll draw the direction of current flow. Current is flowing this way. Current is flowing this way. If I properly draw the current, current goes there. From there, current goes there. Current goes there. Current is first meeting the arrow of the LED. Remember, if current meets the arrow, current can go through. Current can go through. If current can go through, this will light. If current meets the arrow first, current will go through. If current meets the arrow first, it can go through. It can go through. Come to this side. Current comes, goes that side, go there, go there. Current is first meeting the gate. If current meets the gate, remember, current can't go through. Reverse bias. Current can't go through. Current can't go through. So through this diode, current can't go through. Through this diode, current can go. Which means Y is forward biased. If it is a LED, Y will light up. Y is forward biased, Y will light up. B bar. State the reason why the other LED does not light up. Why didn't this one light up? You can tell current couldn't go through, but that's not a proper word. Why the current couldn't go through? Use the proper scientific word. Because this LED got reverse biased. W got reverse bias. Due to reverse biasing only, it couldn't light up. State the reason why the other LED did not light up. It is reverse biased. Reverse biased. The other LED reverse biased. Roman 4. Figure 2 shows how a battery and a switch are connected between A and C after removing two LEDs. Now analyze the question, Lamai. Now analyze the question. Battery is connected, current is given. Magnetic field is however there. Now what will be produced? Battery is connected, current is there. Magnetic field, however there, what will be produced? Sure. Force will be produced. Force will be produced. What rule? Left hand. Fleming's left hand. Using that analysis, we'll start the question. Simple questions. That in essay. Essay is considered hard. In essay, electromagnetism, electrochemistry, electronic like questions are considered hard. Look at the questions coming. A part, state an observation made when switch in the circuit is closed. Put on. Current is there, magnetic field is there. What is produced? Force. What you observe? What you observe? Due to the force, what will happen to the rod? Rod will move. Rod will move. If you want to win the hearts of the teacher who is correcting this paper, maybe you can apply the rule and tell which direction the rod is moving. Apply the rule and tell me which direction the rod will be moving. Try to find the direction that the rod is going to move. If you want, I'll properly mark the direction of current flow. Now, they are not asking the direction. And that way, you can win the heart of the teacher who is marking your paper. From positive, current will be coming. Current comes, current goes there, current goes in that direction. Current downwards. Current downwards. On. Current downwards. Magnetic field is into the boat. Magnetic field is into. Find the direction of the force. Now tell me right or left. It's also hard to tell. You tell me, is it X or Y? Y is extra. We'll apply Fleming's left hand rule. Magnetic field in, magnetic field in, magnetic field in. Current should be down. So your middle finger is down. Current is down. Current is down. Open the thumb. Which direction? Properly apply and tell. Don't tell X and Y both. See, index in, magnetic field in. Current is down. Middle finger down. Middle finger down. Now you open your thumb. Thumb is that direction. Thumb is that direction. Force is that direction. Force is that direction. Force is that direction. That direction is the force. So that direction the rod will move. That's your observation. B part. Name a device made using the phenomenon associated with the observation. Tell me the devices that were using this. The lesson is so easy. Devices that are made using force acting in a current carrying conductor placed in magnetic field. 1. Loudspeaker. Loudspeaker. 2. DC current motor. Ta-da! That is also done. That's also done. Last question. Last question. Before the last question. Before the last question. Yes, less than 1 week is there. 5 days. 6 days. Today also gone. Less than 1 week is there. 5 days are there. Can you do this? That question will be running in almost all your mind. Within 5 days, big exam we are going to face. Can we do this here? Don't allow your mind to even ask that question from yourself. You really can do this, Lamai. That's why you are on this. If you can't do this, you had so many chances to give it up. But you didn't do it. You didn't give it up. Why you didn't give it up? Because you wanted from your end to do this. When you want from your end to do something, Lamai, never do it in a very small, normal way. If you really wanted to do something, Lamai, do it in the best way you can. Lamai, this is one life. This is one you. This your life, this situation you will never get. So this situation, this life, this you, be the best of you. Don't allow it to be a normal way. I'm not only telling for your O level. Hereafter, hereafter, throughout your life. This is one you yourself be the best of yourself. You only can do that to you. No one else in this world, no one else in this world can do good to yourself. Only you can do good to yourself. Only you can take yourself to a higher point. Don't fall into that normal or 99 percentage of the people those are living their life. They just live, they just die. Yourself, take it to the maximum highest point you can. Maximum highest point you can. Don't allow the life to be a flat line. Don't allow life to be a flat line. Take the life to the highest peak point you can and keep on going it. Never allow it to drop into a flat line. Now from this, from your O level, that high peak points will start. Never allow it to drop down. Whatever the potential you all have built now, continuously use it. Don't keep any regret on whatever you do, including your O level. This last 5 days, don't keep regrets and study. Don't keep any regrets. Without condition, without borders, without limits, you study. And finish it in the best way you can. Don't finish it without winning it. Win it and finish it. Now, some fellows will tell, sir, I am not that kind of a person. From the birth, I don't achieve big things. There are people who are talented. Only those people work really well. Only those people can achieve. From my initial days, I'm not this. Nothing after about grade 6, grade 7, until grade 7, grade 8, I was working. After that, I had a drop. After that, I feel I'm not talented. Ehima win nahalamai. Yes, talent is having a part here. But more than the talent, what is important is your effort. That is what is going to give you the success and the achievement. Actually speaking, your success will depend on your talent and the effort. That's true. Your success depends on the talent and the effort. Maybe talent wise you are low. If you put a high effort, you can go for your success. Your success depends on the talent and the effort. Some people from their birth, they can sing. They have that talent. But if you want to polish that singing, you need to again and again practice. You need to put more and more effort to that. Then only it gets polished. Same way. Maybe you are somewhat talented in studying. Your effort will increase the studying percentage. Maybe you are not talented in studying. Your effort will increase your success rate. Your effort will increase your success rate. From that only you go for an achievement. To achieve something in your life, you have to see success in it. That success, again, you have to put some more effort to that. Whatever you succeed, you put some more effort to that, then only you go for an achievement in your life. To succeed, you put effort. To make it an achievement, you put more and more effort. Now finally, Let's say you're good at talent, you're good at singing, you have the talent of singing there. To achieve something in it, you practice really well. From that, you put more effort, then only you can go for achievement. Finally, if we make a single equation from it, your achievement is equal to, if we subject success there, success is talent into effort, that is talent into effort, another effort will come, effort square. That's how you go for your final achievement. These are not formulas that I have made, these are psychologically existing formulas. A person's achievement depends on, yes, talent is there. Talent multiplied by square value of the effort. Let's say there are classroom in your class, A and person B. Person A by birth not talented in studying කියලා ගමු ළමයි. Person B is talented in studying. Let's take person B is 2 times talented than person in studying. Him win නැහැ. There can't be a person who is 2 times talented in studying like you. That much of talent can't be existing in this world. There can't be another person who is 2 times talented in studying than you. Have will take like that. The other person is 2 times talented in studying than you. You are not much talented in studying, but still, you put a effort. You put a effort. You put a effort 2 times the effort that this person puts. Your effort is 2 times the effort that this person puts. Finally, that 2 times the effort will become square value and give you the achievement. That 2 times the effort will become 4 times. 4 times of it will give you the achievement. Basically, your achievement will be bigger than this person's achievement. This person's talent is 2 times. It is less. Your effort is 2 times. 2 times 2. So your achievement will be big. So don't think talent can change the full story upside down. More than the talent, effort will only change the full story upside down. So you put your maximum effort into whatever you do. Whatever the effort you put, it will become 2 square value of it and give you the output. So even if you think like, no, I can't do this, I'm not talented, Kila, remember there is one more thing on your hand, your effort. Your effort matters here, much and much. However much you can put effort. Put effort to this final 5 days. Hurry, come on. Put your maximum effort of it. Maximum effort you put. That maximum will become square value and give you the achievement. Go for that. Don't stop from normal levels. Don't just reside with normal levels in your life. Go for the best place you can. How long are you going to depend on your mother and father? Remember, the life you are living until now, it's a fairy tale life. You're 15 years until the last board of fairy tale life. Quickly going to fall into very important socialized. There you have to accept everything. Whatever your parents showed you, whatever the parents that kept you inside, they kept you inside a well. They showed world is very beautiful. Our family is very nice. We are very good. එහෙම වෙන්නේ නැහැ ළමයි. Very soon you are going to fall into a very socialized life. You have to accept it. Your father, that fellow is already having so much of diseases in him, which he has not even told your mother. Very quickly, so many things are going to change upside down. Your mother, with all the dreams she has, she is just sitting in the house. She has never went for the dream she wanted to achieve. Have you ever asked what's the dream your mother has? It's on your hand to fulfill that. Your father's dream, your mother's dream, all are on your hand to fulfill. You have to take it. They gave up everything for you. Don't tell no. Your mother gave her full life because of you. Maybe they will have some wrongs. Anyone has wrongs. Anyone has errors inside them. No one is perfect in this whole world. Maybe they will have errors, but they tried their maximum to sacrifice their full life for you without doing what they wanted. When are you going to fulfill their dream? This is the start. From the start, go for the best of the best you can. Go for the best of the best you can. Don't stop with that even. Go for the maximum you can. Hurry. Can. Right. We'll finish off the last question as well. Normal life is not for you, Lamai. Normal general life is not for you. You go for the maximum peak you can because this is the one and only life you have. Third question, B. In order to operate a certain household electronic equipment, the domestic electricity supply has to be converted to a low voltage. You have to convert to a low voltage. Direct current electric supply. To convert to low voltage, you need to use a step down transformer. And you have to convert it in direct current. To convert to direct current, you have to do rectification. Rectification has to be done. For that, an arrangement consisting of following parts is used. 240 voltage is converted to 12 volt. Transformer. What's the transformer? Step down transformer. Full wave rectification is used. You are getting direct. Direct current is becoming smooth. Direct is becoming smooth. You all tell me which device will convert into smooth current? Which is the device that makes current? Capacitor. So X should be most of the time a capacitor. What are they asking? What type of transformer is connected to the above arrangement? Step down transformer. In what coil in this transformer should the wires of higher diameter be used? Tell me. Step down transformer. Chuti fellow thick. Keep that in mind. Step down transformer. Chuti fellow thick. So which one should have great diameter? Which one should be thicker? Chuti fellow thick. This primary. This secondary. Fellow thick. Secondary. In what coil in this transformer should wires of higher diameter be used? Secondary coil. State the reason for this. Why? To reduce heat loss. To reduce heat loss. To reduce heat loss. Roman 3. The number of turns in primary coil of the above transformer is 1800. Number of turns in primary is given. What should be the number of turns in secondary coil? Voltage in primary is there 240 volt. Voltage in secondary is there 12 volt. We'll apply the equation. We'll apply the equation. Number of turns in primary over number of turns in secondary equal voltage in primary over voltage in secondary. Number of turns in primary they have given 1800 turns. Number of turns in primary is given 1800 turns. Divided by number of turns in secondary they are asking. Voltage in primary you know 240, secondary 12 volt. 240 volt over 12 volt. Now do the math. First I'll cut off the things. 12 and 240 will cancel off 20. 0, 0 cancel off. Even 2, 180 will cancel off 90. Everything cancels off. Ns is equal to 90. N is equal 90 turns. N is equal 90 turns. Be careful with the mathematical calculation. NP 1800, Ns you need to find. VP 240, VS 12. 12 and 240 cancel off 20, 0, 0 cancel off 180, 2 and 180 cancel off 90, N is equal 90. N is equal 90. N is, N is equal 90. Illustrate graphically how the 12 volt alternating voltage supplied by the transformer varies with time. 12 volt AC. 12 volt AC. You draw a graph. AC current graph. Voltage versus time. You draw it like this, you'll have marks. If you draw it like this, you'll have marks. But they are specifically mentioning 12 volt. No? Make the highest point as 12 volt. This is voltage. Lowest point also 12 volt minus 12 volt. If you mention the values, it's more better. 12 volt on top, minus 12 on bottom. That's more better. Roman 4. Draw using standard symbol how the four diodes are connected in full wave rectification. Sorry. Full wave rectification. Full wave rectification. Full wave rectification, you have four diodes. You connect the four diodes like this. The theory class people, I have taught you how. We'll draw it separately. Theory people, I have separately taught you how to connect the four diodes. Full wave rectification. These two diodes, draw it like this. These two diodes that way. Bottom two diodes this way. Bottom two diodes this way. Top two this way, bottom two this way. That's how you connect the four diodes for full wave rectification. Top two this way, bottom two this way. Roman 5. Name the device indicated by X. What's the device X? Capacitor. Device X is capacitor. Ta-da! With that, electromagnetism also. That. Revise a little bit on electrochemistry. I catched you, however, in Chem night. Electromagnetism today, or a tough section that we couldn't do in a free session is electronic. Go through electronics little bit. With that, those all those three questions you are ready, Kianne, for essay question, any question you can play the game. Biological process of human body අනිවාර්යෙන් බලන්න ළමයි. Together with that, now they are connecting living tissue section. ඒ හින්දා not only biological process of human body, they can get connected with living tissues as well as inheritance system. ඒව ටික පොඩ්ඩක් බලා ගන්න. That finishes us our overall 2024-25 O level. The program comes to an end. The plan was from last year. What are the things? How are the things going to work? Even your seminars, only seminar date we have to put it 1 week delayed because Central Province had the exam until the day before the final seminar. Other than that, everything was planned already 1 year before, including this year's final seminar locations. Same way for the next batches, already the full plan is there. What we are going to do, how are we going to work, when are the night sessions going to start, what we are, what ඔක්කොම plan. Right? Finally, if I give a word for y'all, y'all work like nothing. My WhatsApp messages are like almost then unseen messages only 2,800 are there. Out of that, at least 75% is some of your doubts. Most of the doubts I try to clear. Some doubts I also can't. I'm stuck. Sometimes the messages get missed. Such a amount of doubt asking set කියන්නේ all the That means such a amount of work is done from your end. Super. That's what we want. You personally, most of y'all worked. That I personally saw. Even in our normal classes, They come and ask questions. They do the work. ඔය වගේ a lot of work is done from your end. ඒ කියන්නේ whatever I expected from your end, you all give. I don't know whether I gave my maximum according to your expectation. I'm sorry if I couldn't give my maximum. I tried my level best to give my maximum at all instances. But from your end, whatever I expected, that maximum came from your end. And both of them together will finally produce the result. එහෙනම් y'all should produce result. ඒක අනිවාර්යෙන් y'all should do. This much of work is done from your end, from our end, every side. අනිවාර්යෙන් now your aim is your final aim. Don't aim on small results. Aim big. The biggest result that you can. And for that result you go. Aim big, achieve big. Don't stop until you achieve that. Don't stop working until you feel like you achieve that. Yes, 5 days are there, you work. Don't stop. Sorry. One more point, Lamai. Now, with today, this session will be finishing. At the end, if you can go to the YouTube section and put a comment, whatever you all are sending here, long messages, put as a comment there. So later on a certain day, I can go through them and I can read it. Even last batch comments I used to read still because it remains there. Physics night comments I used to read. Chem night comments I used to read. Whatever you all wanted to send, please send it as a comment there. So I can later on also read it. Just post it there and keep. Hurry. So with that, we have come to the end of our full session. But the final end is there from your end in another 1 week. So with that, wrap up this session in the best way you can. That's what I want from you. Best way you can. Not the normal ways, and the best of the best way you can. That way finish it. Okay. එහෙනම් with this 2024/25 O-level batch comes to an end. Before we finish, I ask you all a question. What do you feel about science now? There you go. Letter by letter. Letter by letter. Letter by letter. Start. P. Next letter. A. Next. T. Next. T. Last letter. A. There you go. Next. E. Next. A. Last two. Yes. And last letter. Y. There you go. Patta easy. Don't forget the hashtag and the signature. Surely we'll be missing you all. I'll meet you all again with the Patta results. Until then, it's your brother, King Sperori, signing off.